Welcome to the second half of the course. In this part of the course, we're going to be studying three-dimensional space, and we're going to be studying vectors, in particular three-dimensional vectors. Now, first of all, the material in this half of the course is going to be absolutely essential if you have any plans to take Math 254, Calculus 4 in the future. But of course, if you're in physics and engineering, knowing how to represent stuff in three-dimensional space is going to be essential just because most of the stuff that's happening in the world is happening in three-dimensional space. Now, we have a lot of learning objectives for today, but unlike in the series and sequences part of the course, each learning objective can be addressed in a fairly short period of time. So, the first thing that we want to do is draw a point in 3D space. Then we want to be able to find the distance between 2 points in 3D space. We want to be able to describe spheres and balls in three-dimensional space. And then we're going to start talking about vectors. What is a vector? What are the components of a vector? What does a representation of a vector look like? And how do we find the so-called components of a vector given information about its length and angle, or given information about its starting and ending position? Graphs in 3 dimensions. When we were in 2-dimensional space, and our points had 2 coordinates, an x and a y, then we could have 2 axes. We had a horizontal axis represented by the variable x, and we had a vertical axis represented by the variable y. The number in the x's position told you how far and in what direction to travel along the x-axis. For example, you might be given a point that has an x-coordinate of +4. The number in the y's position told you how far and in what direction to travel in the y-axis. So maybe your point has a y-coordinate of -1. Then to find our way to this point, we would travel 4 units in the positive x direction, then 1 unit in the negative y direction, and where we landed would be the point 4, -1. In 3 dimensions, if we want to specify a 3D location, we're going to need 3 numbers to do that, which are extended in a natural way along the alphabet x, y, and then z. So we're going to need 3 axes, and here's how we draw it. 1 axis horizontal, 1 axis vertical, and 1 axis coming toward us in perspective. So we draw it at a slight tilt to make it look 3-dimensional, like this line is running from front to back. Now, this may seem a little unusual, but this is the convention, especially from physics. The convention is that the positive x direction is pointing toward us. The positive x direction is the one that is pointing toward the viewer in our direction. The positive y direction is the one that's pointing to the right. And what is the vertical direction? We use the variable z to point up and down. Positive z-axis goes straight up. Now, if you want to draw a point, such as 4, -1, maybe 3, then the 4 in the x's position is telling us to go 1, 2, 3, 4 units in the positive x direction. The -1 in the y's position is telling us to go 1 unit in the negative y direction. The +3 in the z position is telling us to go 3 units straight vertically upward. So if I follow those directions, I'll go from the origin at 0, 0, 0, 4 units in the x direction, then 1 unit in the negative y direction, and then 3 units straight up. And the final position after following those directions, is the point 4, -1, 3. Now in this picture, we do have some special names for some special locations. We, as usual, have the x-axis, the y-axis, and the z-axis. The x-axis is the line that points to us, the viewer. The y-axis is the line that points left to right. And the z-axis is telling you your vertical location, your height. This is the line that points up, down. A plane is basically a flat sheet, sort of like a flat piece of paper. The xy plane is the plane that contains the x and y axes. The xy plane would be the horizontal plane drawn in pink here that contains both the x line and the y line. Corresponding to that, we have the YZ plane, which contains the y and z axis. And we have the XZ plane, which contains the x and z axes. So, to make a quick sketch, the YZ plane would contain y and z. So this is the plane that's standing straight up and facing us. And then for the XZ plane, this is the plane containing the x and z axes. So this is the plane whose edge is facing us. It's standing up and the edge is facing us. Now, as we had in 2 dimensions, the 4 quadrants, which were separated by the 2 axes. In this drawing, we have what are called 8 octants. This is not super important, but it's a word that you may hear going forward. An octant is one of the 8 regions formed by the axes. Finally, we have the origin, the place from which all points are measured. The origin is the point 0, 0, 0 in 3-dimensional space, just as it was the point 0, 0 in 2-dimensional space. Now, when you are considering 2 points in 3-dimensional space and trying to calculate the distance between those 2 points, you can use a formula that's very similar to the distance formula that we used when we were in 2 dimensions. So let's quickly recall what the 2-dimensional distance formula was. If we had 2 points, one which was called x1, y1, and the other which was called x2, y2, then the distance between those points could be found by taking the 2 x coordinates, finding their difference, squaring that, taking the 2 y coordinates, finding their difference, and squaring that, add those 2 results together, and then take the square root of the entire thing. In 3-dimensional distance, where we have not only x and y, but a third coordinate z, the distance formula is extremely similar. Actually, can you guess what it's going to be? In this case, we take the difference of the 2 x's, square that, the difference of the 2 y's, square that, but then we take the difference of the 2 z values, square that, add those 3 quantities together, and take the square root of the result. Let's get some quick practice with this distance formula, where we have the 2 points 3, 7, 1, and the point 2, 4, minus 1. So the distance can be found by taking the square root of the difference between the two x-coordinates, second minus first, the difference between the two y-coordinates, second minus first, and the difference between the two z-coordinates, second minus first. So let's go ahead and calculate these numbers. We have 1 squared, which is 1. We have negative 3 squared, which is 9. We have negative 2 squared, which is 4. So all in total, this is equal to the square root of 14. There is a little bit less than 4 units of distance between these 2 points in 3-dimensional space. So if you walked directly from one point to another, this is how far you would travel. Here is a related question. Suppose that we have an arrow which is drawn so that the tail of the arrow is at the origin and the head of the arrow is at the point 4, 1, 2. What is the length of the arrow? So let's get a sketch of this situation. We have 1, 2, 3, 4 units in the x direction, 1 unit in the positive y direction, and 2 units in the z direction. So if I follow the path given by those directions, I'll end up with a point that is roughly speaking here, the point drawn in red. So the arrow whose length that I'm trying to find extends from the origin out toward this red point. What is the length of this arrow? Well, from the picture, maybe it's easier to see that the arrow's length is exactly the same thing as the distance between the origin, the arrow's tail, and the red point, the arrow's head. So the square root of the second point, where x is 4, and the origin, where x is 0, square that. Then, where y is 1, take away 0. Where z is 2, take away 0. So in other words, to find the length of this arrow, stretching from the origin to 4, 1, 2, we just have to square each of those individual coordinates in the point that's given to us for the head of the arrow, and then add those squares together and take the square root of that. 16, 4, 1 looks like the square root of 21. Still continuing with this concept of 3-dimensional distance, ask another related question. Find an equation which describes any point xyz, which is exactly 3 units away from the center point 1, negative 1, 2. So in other words, we're given a specified distance this time. The distance is going to be exactly 3 units. We're also given a specified first point. We're traveling from the center point out 3 units, but the second point is being left unknown. So let's fit all of this information into the distance formula and see what we come up with. The d in the distance formula can be replaced by 3. The second point, the second x, is being referred to as simply x. X, take away the first x, the number 1, square that. Then y, take away the second y, square that. And then z, take away the second z, square that. This equation describes any point xyz which is exactly 3 units away from this given center location. Alternatively, if you did not like this square root and didn't want to keep it around, you could say that such a point xyz has to satisfy the equation 9, squaring both sides, 9 equals x minus 1 squared, y minus negative 1 squared, z minus 2 squared. Now, can you describe the shape that is formed by the set of all the points x, y, z, which are exactly 3 units away from some central location? Let me indicate the center point with a dot. From this point, we can travel 3 units in any direction: up, down, left, right, front, back, or in any combination of those directions. For example, you could also head up and to the left. The set of all points which are exactly 3 units away from the central location form a sphere. So this is how I usually draw the sphere. I draw one upright circle around the center, and I draw a little tummy, a little stomach around the center, to indicate the fact that it's 3-dimensional. This is a sphere, in this problem, of radius 3 units, since we're 3 units away from the center being the point 1 minus 1, 2. Taking that exercise and generalizing it, we can get a general formula for the equation of a sphere centered at x naught, y naught, z naught. All the points in the sphere satisfy the equation the radius squared is equal to x minus the x of the center squared, y minus the y of the center squared, plus z minus z of the center squared. A sphere centered at x naught, y naught, z naught is the set of all the points which are a fixed distance from the center. So basically exactly the same as the equation of a circle in 2-dimensional space, except this time, since we're in 3 dimensions, we do have this third term. Now a ball centered at x naught, y naught, z naught is basically just a sphere that has its center filled in. The equivalent to 2 dimensions is we had a circle versus if you filled in the circle and considered all the points on the inside as well. The difference between a sphere and a ball is similar. The sphere is just referring to this outer shell where the points are exactly r units away from the center. But a ball contains the sphere and everything inside the sphere. So balls are usually described by an inequality, where the distance between the point and the center can be anything less than or equal to r squared. Let's go ahead and let's find the equation for the sphere of radius 2 with a center -5, 1, 0. Then let's find an inequality for the ball of radius 2 with the same center. So the sphere, all we need to do is take x minus the x of the center squared plus y minus the y of the center squared plus z minus the z of the center squared and set that equal to radius squared. This is the equation for the sphere of radius 2. It can be simplified if you want, but that's not required in this problem. Whereas the equation for the ball of the same radius, well, it's not even going to be an equation anymore as such. We're going to have x minus x of the center squared, y minus y of the center squared, z minus z of the center squared, that distance, can be anything less than or equal to radius squared. Anything on the shell or closer in toward the center. Oh, I think I already gave this earlier. See above? Now sometimes you're given an equation for a sphere that's not quite in the correct format to make it easy to see the center and the radius. Sometimes some modification needs to be done, as in the following example. What is the center and the radius of the sphere with the following equation? X squared plus 6x plus y squared minus 4y plus z squared plus 8 equals 11. The big difference between this equation and the equations that we had in the previous examples is that our equation has some variables which are not contained inside of squared quantities. In the equation for the sphere, the variable x, the variable y, and the variable z always appear within a squared quantity. But in this equation, we have stuff like 6x and negative 4y, which are instances of a variable which are not inside a quantity that's being squared. So what we're going to do is we're going to complete the square, which is a term from algebra which is telling us to rewrite an expression so that all the variables which are outside of squared quantities are tucked inside of squared quantities. To complete the square with the 6x, to take that quantity and tuck it so that it's inside of a squared quantity instead of being outside in the open here, the idea is to take the coefficient 6, cut it in half, and then square it. And then add and subtract it. Or if you prefer, add it to both sides. So half of 6 is equal to 3, and 3 squared is equal to 9. So I'm going to add 9 to both sides of this equation. Now for y, we have y squared minus 4y. So that negative 4y, which is outside of a squared quantity, is what's causing the trouble this time. So I'm going to take that number, negative 4, cut it in half, and square it. Negative 4 squared is minus 2. Minus 2 squared is plus 4. So I'm going to add 4 to both sides. Now z seems to be doing okay. Z squared, the only copy of z, is inside of a squared quantity. And then I have the plus 8, which I'll move over to the other side with the rest of the constants, 11 minus 8. Now the reason that we add this quantity, half the coefficient squared, is because now it gives us the ability to factor this as x plus 3 quantity squared. The 3y terms can also be factored as a perfect square. This becomes y minus 2 quantity squared when those three are factored. Then we have z squared, which didn't have any problems. And on the far right side of the equation, we have 11 minus 8, 3. 3 plus 9, 12. 12 plus 4, 16. So we can see that we have x minus negative 3 quantity squared. So our center will have an x component of negative 3. We have y minus 2 squared. So take away 2. 2 is the y coordinate of the center. We have z minus nothing squared. So since nothing is being subtracted from the squared z, the z of the center is 0. And finally, the radius is the number whose square is 16. 16 is 4 squared, so the radius is 4. And so that is how we can find the center and radius of the equation of a sphere, which is not necessarily in this standardized format. We can complete the square using algebraic techniques in order to convert it into the right format. Now with that, we're going to start to talk about vectors. Now, a vector is just any quantity any piece of data, any piece of information which communicates both a direction and a length or strength or magnitude. For a familiar example, let's go over to real life. One of the quintessential examples of a real-life vector is a force. A force is a quantity that both has a direction and, in this case, it has a strength. For example, suppose that you go ahead and you take a small object, maybe you take a cardboard box. You take a cardboard box and you push on it. When you push on the box, first of all, you're pushing on the box in some direction. You might push on the box straight down from the top, or you may be pushing the box on the side in order to move it horizontally, or you may be applying the force vertically, lifting up from the bottom. That force can also be applied with various strengths. You may give that box a really hard shove, and that would be a force with a lot of strength, a big magnitude, or you may give it a light tap, and that force would have very little strength, a very small magnitude. The strength of a force is officially called its magnitude. So any force is a vector. It's a quantity that has both a direction in which it's being applied and a strength at which it's being applied. We can also think of any straight line motion or travel as a vector. In this case, the direction is the direction of travel. And the length that is being communicated is the length of the travel itself. How far you travel. Additionally, we have velocities. A velocity is the term for when we communicate the direction of travel and the associated size or length of the vector is what's communicating how fast you're traveling. For example, if you look at two different cars, one car may be pointed in the direction to the east and may be traveling in that direction, and another car may be traveling in the north direction. Maybe the first car is traveling only at 30 miles per hour, but the second car is traveling at 50 miles per hour. So the velocities of these cars communicate both the direction in which they're traveling and the size magnitude is how fast they're traveling. Now, mathematically speaking, a vector from a mathematical perspective is really just a finite ordered list of numbers. That would be the mathematical definition, as opposed to the one given up here, which is more of a physics definition. But you won't really be getting into the mathematical perspective on vectors until/unless you take Math 240, which is the class called linear algebra. Now, when we represent unknown quantities in mathematics, we represent them using letters. But there are traditional ways of representing different quantities. For example, we usually use A, B, and C to represent unknown constants. We usually represent variable quantities, variable numbers, by X, Y, and Z, and we usually represent functions by F, G, and H. This is traditional. And likewise, there are traditional ways to represent vectors. First of all, vectors are usually represented using the letters U, V, and W. But not only that, to really communicate to the reader that the quantity that we're working with is a vector and not just an individual single number, we usually emphasize that by putting a vector arrow over the letter. So U with a little arrow on top, V with an arrow on top, W with an arrow on top. This is sort of like how we usually say not just F, but F of X, to emphasize the fact that that quantity is a function of X. We emphasize vectors by using an arrow on top of the letter. The reason why vectors are indicated with this little arrow on top of the letter ties into how we represent vectors visually. Visual representation of a vector is we write them as arrows. That's because arrows are quantities with direction and with length. The direction of the arrow represents the direction of the associated vector. And the length of the arrow when you draw it, captures the length, strength, or size of the associated vector. For example, let's visually represent a vector with the following specs. I want a vector whose length is exactly the square root of 2 units. And I want a vector which is pointing in the direction corresponding to the angle 45 degrees. I should specify that this is going to have to be a 2D vector. For a 3-dimensional vector, it's not possible to specify its direction with a single angle because you can angle yourself horizontally or you can angle yourself vertically. So you need a minimum of 2 angles to specify a direction in 3D space. So a 45-degree angle, measured according to mathematical convention, is measured from the positive x-axis counterclockwise. So the arrow that I'm going to draw is going to be somewhere along this ray. I want to draw an arrow which is precisely square root of 2 units. So I can indicate that by drawing a square root 2 next to the vector in the picture. Or I can note the fact that a vector of square root 2 length pointing in the direction of 45 degrees can be achieved by going 1 unit in the x direction and 1 unit in the y direction. We can confirm that if we take the distance between the tail of this arrow at 0, 0, and the head of this arrow at 1, 1, that the result will be equal to the square root of 1 plus 1, which is in fact the square root of 2. Now, just as a vector with a specified length and direction can be represented graphically by an arrow, it also is convenient, usually more convenient, to represent a vector symbolically. So if you ever see a notation like this, where you have an angle bracket, a number, comma, another number, angle bracket, this refers to the vector with such a length and a direction that if you started drawing the vector at the origin, if you travel along the vector AB, your terminal point, the head of the arrow, would point to the location A, B. So the vector angle brackets A, B is the vector which stretches from the origin to the point parenthesis A, B. So I just want to emphasize that A, B with the parenthesis basically represents a destination. The final location of the arrow, the terminal point, the stopping point. Whereas the notation where you have the same AB, but instead of parentheses you have angle brackets, this is more like the journey. This is representing the entire travel from the origin to the destination at the point AB. Of course, there's a three-dimensional equivalent to this as well. If you see the vector ABC with angle brackets, if you start drawing the vector so that its tail is at the origin in three-dimensional space, the head of the vector will be at the point ABC in three-dimensional space. Let's consider the vector angle bracket -1, 3. Here it is represented symbolically. Let's go ahead and create a graphical representation of this vector. So the head of the vector has to be right here. So going in and drawing the vector stretching from the origin to the point -1, 3, this orange vector is the vector -1, 3. Now, how long is the vector? The length of this vector can once again be calculated using the distance formula, in this case for two-dimensional space. We can take the square root of the terminal point minus the initial point, -1 minus 0 squared, 3 minus 0 squared, which coincidentally is the same thing as -1 squared plus 3 squared, which works out to be the square root of 10. That is the length, the size, the strength of the vector -1, 3. For a three-dimensional equivalent, let's sketch the vector 1, 2, 4, and let's answer the same question, how long is the vector? I need to travel 1, 2, 4 units. In the x, y, and z directions respectively. And then the vector 1, 2, 4 stretches from the origin out to that point. How long is the vector? In this case, we can use the three-dimensional distance formula for the distance between 1, 2, 4 and the origin 0, 0, 0. Which, just like last time, will reduce to 1 squared plus 2 squared plus 4 squared, which is equal to the square root of 21. That's the length of this vector in this case. Now, these numbers which show up between the angle brackets when you're representing a vector symbolically, do have a special name. These numbers are called the components of the vector. For example, in the vector 1, 2, 4, 1 is the x component, the component of the vector in the x direction. 2 is the so-called y component. And can you guess what 4 is going to be called? 4 is the so-called z component. So let's practice finding the components of a vector given the information about its length and about its angle. So once again, I'm referring specifically to vectors in two-dimensional space here. So 5 pi over 6 is just a little bit short of pi. So that angle is going to place us in quadrant number 2. And we want to draw a vector which is 3 units long, starting from the origin along this ray 3 units. So the question is, where is the terminal point of this vector? Where is the head of this arrow located as drawn starting from the origin? Now, the formulas that we need to find the location of this point are the formulas that you probably learned in pre-calculus 2 or in trigonometry. We have the fact that the x-coordinate of this point can be found by taking the distance 3 and multiplying it by the cosine of the given angle. 3 times cosine of 5 pi over 6, which, if I recall correctly from my unit circle days, cosine is negative root 3 over 2 at that angle. The y component of the vector, which is equal to the y coordinate of the terminal point, is the same thing except with sine of the angle, sine corresponding to the y value. So in this case we would have 3 times, I think, positive 1/2, 3 over 2. So then, what are the components of this vector? How would I represent it symbolically? The vector components are angle bracket negative 3 root 3 over 2 in the x position, and the y component of the vector is 3 over 2. I want to construct a formula for a two-dimensional vector with a specified length, let's call it capital R, and a specified angle, let's call it theta. Then I can just go ahead and take the specified length, multiply it by cosine of the angle, and the specified length, multiply it by sine of the angle, to get the x and the y components respectively. Another way to describe a vector is to describe that vector as an arrow, but not necessarily drawn with its tail at the origin. A vector communicates both a length and a direction, but that vector could theoretically be drawn with any starting position. Drawing it at the origin is conventional, but not required. The vector being described here has the tail at 2, 4, and the head at 1, 7. So the question is, what are the components of the vector? In other words, if you drew exactly the same vector, not originating from the point 2, 4, but instead originating from the point 0, 0, where would the head of the vector end up? To get from 2 over to 1, the x decreased by 1 unit. To go from 4 up to 7, the y had to increase by 3 units. So if I drew exactly the same vector, starting from the point 0, 0, I would draw it decrease 1 unit in the x direction, increase 3 units in the y direction. And where would those directions take me? It would take me from the point 0, 0 to the point where x has decreased by 1, giving me -1, and y has increased by 3, giving me +3. -1, 3. Now there is a way to quickly get the components of the vector without having to go through the process of drawing the vector and moving it so that it originates from the origin. This is especially useful in three-dimensional space, where drawing vectors accurately can be a bit bothersome. So if you want to find the components of a vector, with the tail at a point which I will call P, and the head at a point which I will call Q, first of all, this vector is sometimes written the letter P next to the letter Q, and then an arrow pointing from P toward Q, to indicate that P is the initial point and Q is the terminal point. If these points happen to be two-dimensional, then the vector from P to Q can be found by taking the final x position, taking away the initial x position, taking the final y, and subtracting the initial y. Now notice here that order really does matter. If you mix up P and Q, if you mix up the head and the tail, if you mix up the initial and terminal point, if you mix those up, then you run the risk of one of your components being the opposite of what it actually should be. So order really does matter. The terminal point has to come first, and then you subtract the initial point. In 3 dimensions, the formula is very similar. It extends in a very natural way. In this case, our terminal and initial points also have a z coordinate. And the vector stretching from P toward Q has its x component, terminal minus initial, y component, terminal minus initial, and z component, terminal minus initial. Once again, it's essential to get the order correct. So this concludes the material for today. We introduced three-dimensional space, and we talked about how it's represented visually, in particular how points are drawn in three-dimensional space. Then we introduced the distance formula in 2 and 3-dimensional space, and looked at how that distance formula had consequences in terms of the equation of a circle in 2D and the equation of a sphere in 3D. Then we introduced vectors. Vectors were quantities that communicated 2 pieces of information, not just a length, strength, size, but also a direction in which that length, strength, size was being applied, a number and a direction. And then we practiced drawing vectors and representing them symbolically using components. We found the components of a vector given its length and angle, and we found the components of a vector given its initial and terminal points.